In this presentation, we will discuss how to find a confidence interval for population mean when population standard deviation sigma is not known. For finding the confidence interval for population mean when sigma is known can be found in another presentation. Previously, we have worked on this example of estimating the average number of cars sold by used car salesperson. In this example, the population standard deviation is given to be 15, but in practice, the population standard deviation is an important statistical property of the population, so this piece of information is usually difficult to have or difficult to calculate. What usually happens is that instead of having the population standard deviation, we have the sample standard deviation, as seen in this revised example. Because population standard deviation is not given to us, we would have to replace it using the sample standard deviation, that is small letter s. We lost an important piece of information about the population. We would have to pay a price to attain the same amount of confidence level. Previously, we have discussed that when population standard deviation sigma is given, the multiplier in the confidence interval calculation is a z-multiplier, that is 1.96. When population standard deviation is not given, the multiplier increases to 1.984, and that's not a z-multiplier from the z-table anymore. It's a t-multiplier right out from the t-table. You may also notice that this time, when the population standard deviation is not given, the 95% confidence interval becomes bigger compared to the confidence interval when the population standard deviation is given. Looking up the t-multiplier from the t-table is quite similar to looking up the z-multiplier from the z-table. First, we would have to find the degrees of freedom, which is just the sample size minus 1. Then, for a 95% confidence level, the middle portion under the curve is 95%, and the two corners are 5% in total, so each corner is 2.5%. We would have to rate the corresponding t-score with an upper-tailed probability of 2.5% from the table. For our example, sample size is 100, so the degrees of freedom is 99. From the t-table, we can see that the t-multiplier is 1.984 for 95% confidence level. And for 90% confidence level, this t-multiplier would reduce to 1.660. It is important to know that the z-multipliers are always the same, whereas the t-multipliers are going to be different for different degrees of freedom. Let's summarize the formula for the confidence interval for the population mean when the population standard deviation sigma is not given. It is the same to the previous formula we learned, except replacing the z-multiplier by a t-multiplier, and replacing the population standard deviation by the sample standard deviation. After we find the t-multiplier, we could put all the information we have into the formula and obtain a confidence interval. The interval estimate we get is between 72.02 and 77.98. For sample size problems, we have also derived a similar formula as before. Although we have discussed that for confidence interval calculation, when population standard deviation sigma is not given, we would use a t-multiplier. However, for the sample size problems, it is the t-multiplier that's being used. The reason is that when we work on sample size problems, we do not know what sample size n is. Without knowing sample size n, we do not know which degrees of freedom we should use for the t-multiplier on the t-table, as degrees of freedom is sample size minus 1. Therefore, we would have to use the z-table instead. And this is a fairly reasonable assumption because when the sample size is large, it can be well approximated by the z-distribution. The answers to this example can be found on our course page.